and thank you for tuning in. Welcome to a new episode of the Passion for Technology podcast by EBV Electronic.
Welcome to the Passion for Technology podcast. Technologies such as the Internet of Things would be almost inconceivable without continuously shrinking electronics. Today, there are electronic components in the 100 nanometer size range, but these are digital components. The situation with analog ICs is different. Our guest today, Armin Dapmans, is General Manager Semiconductor at Toshiba Electronics Europe. And Armin and I will be talking about this. Hi, Armin.
Hi, Mustafa. Nice to talk to you today.
My pleasure. I'm super excited about this. Armin, why are analog ICs not shrinking at the same rate as their digital counterparts?
Good question. Everyone is used to look into shrinkage of SoCs because that's the long years trend of trying to decrease the individual design elements, which is kind of very clear shrinkage process. When you look into more analog designs or even power-related elements, then you've got to consider very different topics. And that is, if you look to an analog process, when you talk about shrinkage, then it's maybe not the right term because you look primarily into the design blocks and how they are built. They shrink differently. It means basically you have to understand how to change the design itself. It's not just the individual element, which is the key driver. It's basically intelligence of the design and the related design blocks, or some of the stages that you look into that relate to power. And also power has a different way of shrinking or following the path of miniaturization.
So why is miniaturization of analog ICs so important? What are applications where this is required?
Yes, if you look into the history, this is, I think, an often referred to topic. The general requirement that came along when people were really considering to shrink things is when it came to reduce power, the sizes. If you look into the industry of how you have been creating portable devices, you had to reduce power and at the same time shrink the size of it. And there are so many elements related to that, and that carries on into the future because you try to optimize as much as you can the reduction of power, therefore the reduction of sizes, because there's a direct correlation between the two. If you cannot reduce the power, it's very difficult to shrink the size. When you try to get away with the power dissipation, you have to think about the cooling elements that also have a particular size. And also finally, when it comes to things that move, you try to reduce weight. And so there's a very logical influence. And that is really the driving point, even in today's industry, for so many various applications.
I mean, when we look at increasingly smaller chips, what type of solutions has the semiconductor industry developed to enable that type of continued miniaturization? For example, what role do integrated solutions play?
There are several aspects to this topic. One of this is the base technologies, as we just referred to, because you have to develop that permanently and understand in your basic processes how you do the basic enablement of the shrinkage. When you look into the integration levels, then you come across various other elements. And that basically is how can you integrate things? And when you look into the analog and power-related components together with maybe digital devices, is on the design basis looking at the process. Can the processes be merged? And that involves creating different libraries, for example, different processes that allow for the mixture. And when you look into the highest level of challenge, when you want to integrate digital plus analog plus power into one device, that is the highest level of challenge. And that's what companies like ourselves look into, is like how to enable that. And then when you look into the topic of why don't you, for example, advance in the same way in the analog side with the processes that you do on the digital side, is you have to equalize that element of different requirements. And then the newest technology is not always the most helpful if you start to integrate all these elements. You have to then look into a common base that is basically the most meaningful sweet spot for that kind of consideration.
Speaking of analog ICs, can you give us an idea, our listeners, and, from my understanding too, of what type of sizes or what kinds of sizes can be achieved when designing and manufacturing analog ICs?
I would like to answer that in two ways. One is the basic size element, what you see as a final package that lands on the PCB or even as a die, because that is another consideration. Package design is one thing that we are very much concerned about. And I give you one example. When you look to smaller components like SMOS, then you can, let's say, achieve something like a size of 2 by 2 by 0.75 millimeters, which is very small. Even in one of our major lineup components, like the motor control driver ICs, they land into conventional SSOP 16 packages that have a size of 5 by 6.4 by 1.2, or QFN 16, which is a common package which has a size of 3 by 3 times 0.9. But one thing I would like to highlight is, we were talking about the level of integration, is how much you can actually bring into such kind of package. It's not only that you need to drive down the package design itself, but you really have to care for on how you basically achieve with all what you do, the integration levels into a given package. That is, I think, for us, one of the biggest challenges, that we try to optimize that from that design perspective to achieve the highest levels of integration.
Designing ever so smaller packages, isn't there an increased risk of overheating coming with that? Or is that being alleviated by new materials like SiC or GaN?
Well, of course, the factors that we always look into is, for example, when we look to more the power side of things, then switching speed as well as the ohmic losses, which is basically driving factors for things like SiC and GaN. That was the primary element to push that switching performance up, and also then to reduce the overall losses. But when I was looking into that, it is more also an issue of how you understand the integration levels from algorithm point of view. If you try to integrate a processing element, on the other hand, if it comes to IC design, or you build in firm structures that an algorithm is built in hardware. That is also one of the, let's say, other types of considerations that we have. Especially, I mentioned that once we look at the highest level of challenges, logic side plus analog side plus power side, we also need to consider the algorithm side, in which way we're going to build it in. Do we have an MCU that you can freely program, or do you have a kind of hardwired type of algorithm that lands into the device? So that is the other part of that plays into this.
I mean, would you say that miniaturization of analog ICs has already reached its limits?
No, very clearly. I picked one slogan up from a totally different element, and that person always said, only the sky is the limit. And that is really, I think, the way I would see it, because we have got so many years in front of us. And if you look back as to where we've started in the industry and where we are now, I think no one could ever imagine that we would arrive at the levels of where we are today. And that's why I said, is like companies like ourselves, we have to look into the whole range of things that enable miniaturization, like the field of creating new materials. Wide bandgap is only one of them. We also in our company look into substrates and so on. So materials is a big topic for us. But also then the whole process, how do you design it? How do you bring technologies together? How do you come up with design methodologies and ways to optimize the processing of those elements, as I meant, if it comes to kind of computing elements, or moving items from analog to digital world? That is also a process where then you have more options, but then you are worried about if you can achieve the same parameters. And that gives us a kind of playground where we act within. And that is really, I have to say, there's so many options available for us to strive further in the way of miniaturization.
That would have been my next question, right? But you've already introduced that to a great breadth to us. So let's maybe move on to look a little further out into the future. I mean, where's the trend heading in terms of size? And what would you say what the future looks like?
I think as I mentioned at the beginning, like digital way of shrinkage is one of the things. I think more people look into the way of this integration across the various technologies, but also in analog and power. I think what you've seen that what is happening right now, that new materials come along in the power era, then also the people also look into the improvement of the existing technology. So, for example, when it comes to transistors, we also have in the high voltage MOSFET area this superjunction process that we permanently improve. So also there, we look into increasing switching speed by introducing a high-speed diode that helps the whole process of switching, introducing the losses. And that is also valid for the low voltage process area, because there, if you look, for example, in the way of the electrification topics that go on, let's say there are so many motors required that run at highest efficiency, and also the entire drive circuitry that sits in front of that needs to be optimized. So that means we are looking into ways on how to reduce the overall path of the losses. And that means you look into what you do in the chip itself, what is happening in the whole conductivity area between the chip and the package, and from the package onto the board, or from the die directly onto a board. So that is a whole area of different things that we look at. And that is basically where we play within. The other element, I would like to give you one example. I already mentioned the area of motor control driver ICs, but there are also these intelligent methods of trying to integrate things. And there are two examples we have. I take some acronyms here, so-called ACDS, which is an advanced current detection system, which integrates the shunt resistors into the design that are in many other solutions outside. Or we have a different method. For example, we call it ADMD, Advanced Dynamic Mixed Decay, which achieves a constant current throughout current control. So that is a method of how you do things. And there are so many different examples of that where we are basically executing the whole path of various developments. You see that actually in all the new roadmap releases, that there are new features coming out and how you try to either integrate more, as we already talked, or you do things in a much more intelligent way. And that is which drives the introduction of new products.
I mean, how do you see the transition from superjunction solutions towards wide bandgap? SiC diodes, MOSFETs. What support do you plan, and how does the market develop?
Actually, that has been often talked about. The way to wide bandgap is a way where you have to consider various elements. One is, of course, that you try to strive to maturity. So it means production. You try to achieve the highest quality, reliability, and also high yield so that the cost can come down. That is one of the areas. The second one is the adoption to the application requirements in terms of how you set your lineup, with different requirements related to, for example, our own values. What is the granularity that you need to have in your lineup? Also the various packages that need to come along with this. But back to your question is like, what's the path towards that? We know that it takes possibly 5 to 10 years until wide bandgap comes into the area where you see the revenues that you have with existing technologies today. So, but this is a very steep path. And we know that this has been already started. So people are actually using those devices. And the people are now moving from the first era of trying to just replace some of the older technologies, now moving to the area utilizing the true benefits of all those semiconductors in order to increase the performance. Because in the beginning, the people were not able to really control those kind of hot semiconductors. And now you had to understand basically how to create appropriate control schemes and gate driver devices that enable to maximize the performance alongside with all the other elements that I've already mentioned.
Thank you. I mean, I found this very, very insightful. I mean, in breadth and in depth. Our tradition with our podcast is that towards the end of it, and we're getting there, I mean, we ask our guests for how and when their individual passion for technology developed. And, you being the general manager of a semiconductor division, I'm very, very certain that at some point, probably very early in your career or life, developed a deep passion for technology.
Yeah, I think that is the fascination that I picked up when I saw how companies have been really constantly and in a very high speed been able to improve the miniaturization and the integration levels. It is like what I mentioned at the beginning, also this trend of how people were able to bring out new solutions like that the consumers were using or the people are using in the industry. And that was running in such a high pace that I was so fascinated with that. And I saw Toshiba as being one of the companies that did a lot of inventions right from the start of this process They had a lot of first-time worldwide introductions of new technologies, and we brought out so many different technologies in very different device areas and applications. So that was, for me, a very fascinating area. And that is something where I see and look into all the R&D activities, what is happening, what the people are considering. This is really, really still exciting, and a lot of things to come.
Great. Dear listeners, if you'd like to get in touch with Armin, feel free to reach out via LinkedIn. You can find all relevant links in our show notes. And also, please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Thank you again, Armin, for joining us and for sharing all those insights and personal stories with us.
Yeah, thank you very much. And I really appreciate today's podcast and looking forward to the next version of it. Thank you.